Q&A, no questions.
With the GoToWebinar, used to only have broadcast on demand, so slightly different.
Oh yeah, okay. Chat, open chat. Okay. Okay, I haven't got a response from the chat yet.
Okay, everyone, so we're looking to start in nearly 4 minutes. Farad, you can see my screen?
Yes, I can see your screen, yeah. Good morning, everyone. This is Parag from ITBI. Welcome to today's webinar. We are going to basically today cover 5G functions in HTZ and basically go through some of the challenges, especially in the 3D modeling of the basically propagation and also the features that in 5G, how we can go about solving these different issues and also the planning of 5G networks. So today's presenter is Yahya, and most probably you are familiar with Yahya, so many years in the industry. The way we're going to basically present today, Yahya will be presenting the topics, and then during the process presentation, if you have any questions, you can basically send through the chat. You can send your questions, and then we'll try to answer it as soon as we can. And for the most common questions, probably towards the end of the webinar, we'll go through the most popular questions. So.
Okay, Farad. Can't hear you anymore.
Hello, can you hear me?
Yes. All right.
Yeah. Okay.
Let's kickstart the webinar. So first off, my name is Yahya, guys. So I will be running this webinar for roughly 1 hour. Okay. So we're going to stick to 1 hour as much as we can. There's a range of topics, very interesting topics, and very practical issues we are proposing today. So let's start with the topics. So what topics we're going to talk about? So this is inspired by a couple of studies that we recently been working on, and it seems that when we receive data from operators, we find it a bit challenging. So we're going to talk about that challenge. We think it's straightforward, but actually it's not. So first we're going to talk about in the topics today. First we're going to talk about network importation and antenna placement. So I'm talking about sector, where to put the sector on the building. So this is something very, very interesting in 5G or also in 3D modeling in general. So we're going to talk about importation and modeling 3D antennas, and then we're going to talk about antenna, which is smart antenna and power modeling. So we're going to talk about specifically the broadcast beam, how to manage and how to model the broadcast beam, which is very important. Then we move on to 5G numerology. We move on to SS-RSRP, coverage predictions, and which is the practical aspects of the predictions and planning. And then in the second section, we'll be talking about statistical analysis. This is extremely important. We have a tool which is also a GIS software. So the tool is a planning tool and a GIS tool, and this is something extremely important because you want to do, you want to crunch the numbers, you want to do analysis, so you need to have the capacity to do GIS analysis. All right, and we have throughput analysis, massive MIMO configurations, and carrier aggregation. Towards the end, we'll talk about neighbor planning. Sorry. And we're going to talk about coverage exportation and online publishing, how to publish the coverage online. So let's start with the challenges. 3D challenges, or start with the importation actually. So the tool has a very simple importation mechanism. So we can actually receive a CSV from operator or from carrier. We can import the CSV file, and then we can so CSV file can be in any format. So you have columns, and in these columns you have information such as longitude, latitude, antenna height, frequency, bandwidth, azimuth, antenna gain, transmission power, and antenna name. So these are the minimum information you need to have in order to build your model. So this information needs to be supplied in a CSV or Excel format. And the tool has a very, very simple capability to import this. We're not going to talk about too much, but you can see here the drop menus. So we can match every column with the proper parameter and software, and then we can import. So don't worry about importation. It's something straightforward. So it's not too hard to import information from CSV. So once you import it, it will come to the map as is. So they will be imported on the map, and sorry, my post is gone. So they come to the map, and then in the map they will fall in different spots. Hopefully, they fall in the right spots. You can see here we have lots of sites. These sites were randomly generated, actual sites, and you can see you have 3 sectors per site. So let's see what kind of problem we are facing. So by closely examining, so here they look all innocent, they look all good, but when you go and you dig deeper, you zoom in and you check every site, you'll find something is odd. For example, this site here, you can clearly see sector number 3, the one at the bottom here, is pointing to the rooftop. So this site is on the rooftop, and they've got 2 sectors here pointing different directions, cleared, but this one is not cleared. That's the problem. You can't proceed with a model like this. If you do, you will lose coverage of this tower, or of this sector specifically. This is another site. What's wrong with it? It seems okay, but actually it's not. That site is falling on a high building, and that building is maybe 50 meters height. But when you look at the antenna height, it's only 10 meters. So this is not on the rooftop. What is going on? If you go and you do coverage predictions, you'll find that this site has no coverage at all. It's blocked. But we know for sure it's not indoor. It's not an indoor site. All the model is based on outdoor. So there must be something is wrong. So you need to be careful with this importation process. Don't just take it for granted. You need to dig deeper and see what's going on. So let me shed light on these common issues, common challenges we come across when we do sector placement in 3D. So in 3D, you have the building structure. Okay, so you've got a height of the different rooftops in the building, and then when the antenna falling on the building, you need to be careful where it is falling. If you move it here just 1 meter, it might fall on this smaller section of the building instead of the higher one. So the antenna can be placed. It can be in the middle, and if you put it in the middle here with incorrect height, then you see the signal will be obstructed. It will be diffraction examined here. If you put it in the right spot, say at the edge here, and I'm assuming that's the right spot, you see you've got now nice clearance. This could be on the side of the building, or could be on this side of the building. So you need to have accurate input in order to place it correctly. So where these inaccuracies come from? They come from multiple sources actually. One source is the vertical and horizontal. Of course, the error can be on the horizontal or vertical planes. So you might have vertical error in terms of the height. That height could be from the building itself, error, or from the source. They produce to you, say, inaccurate antenna heights in both vertical and horizontal planes. It could be also sometimes rough coordinates. What they give you is the rough coordinates. They don't give you the actual coordinates of every sector or every antenna. They won't give you, they say the site. The site is on the roof. Well, you don't know where exactly the antennas are placed. That's a very rough way to model it. It could be not necessarily maintained. What we found is sometimes they don't care because they've been using medium resolution maps over time, and then they don't have this problem in the first place because they're using medium resolutions and lower resolution maps. So in the lower resolution maps, you don't have building there to worry about. So in the 3D environment, it can be challenging. There could be sometimes minor discrepancies or errors between the 3D dataset and network parameters. So anything can give rise to a problem like this, and you have to be careful. Now, I'll give you an example here. So when the site is on the rooftop, what does it mean? Is the antenna placed in the middle of the roof, or is it towards the edge? So you need to, it could be actually in the middle. There might be a tower in the middle of on the building, a small tower. Very common, you might see skids, you might see towers, small towers. So it could be actually in the middle of the but it's elevated in that case. So you need to be able to discriminate and then differentiate of these different scenarios. Is the antenna elevated or is it sinking below the roof height? So all these questions, all these challenges can be a problem in planning. Is it on if it is on below the rooftop height? Is it on the far side of the building like what we have here? It's under the building height. It's at the edge, and it's only on the edge by maybe 20 centimeters. But this is important we establish, okay? So let me show you the three different problems that you might come across, or the three different situations that we are talking about. So you might find that your sector antenna height is exceeding the building height, and if it is exceeding, shall I keep it in that spot, or shall I push it to the edge? So if you have accurate coordinates in the first place, then it's not a big deal. But if you don't have if you have rough estimates of the sites, then you have to make a decision about this. And you have maybe 5,000 sites. You're not gonna do it one by one. So you need to find a strategy. You can see here that actually here the antennas are on the side of the building, on the fair side, and in this case here it's elevated above the rooftop. So it could be different cases. It could be case number one, where you have to push it to the edge, like this one, or it could be case number two, where it's actually on the rooftop and it's exceeding the rooftop height. Then we believe it's a cleared antenna. Or it could be something like this, number three. So you've got the site or the antennas deployed on level 1 or level 2, and then they are pushed to the side of the building. So we need to be able to correct this. And this is actually this is a real example. So you've got here antenna camouflaged, and it's on the side of the church. So this is something maybe not managed properly because they didn't pay attention too much for it in the past. So how do we overcome this problem? So in the tool, we have a very, very nice function. I mean, previously we had to export the clutter height of every site, and then compare it to the site height, and then make a comparison and make correction. So today, the tool have a built-in isolation function or filtering function. That filter can tell this case, the indoor case, from the outdoor case. It can tell, and then we can isolate them, and we can target them and attack them. So you don't have to waste your time examining every single site. So you can run that function, and that function will automatically establish, based on the height of the building and based on the height of the site or every sector, where is it sitting? Is it outdoor, or is it actually sinking inside the building? Then we have to do something about it. So what to do about this? This is a very, very useful function, and trust me when I say it, it makes your life a lot easier. So we call it a breakout station. So breakout station is going to convert image number 1 at the top, image number 1, into the image number 2. So what happened here? So you see here previously that site had the 3 sectors were given to be the same spot, and we know it's not correct, but simply because they did not supply individual antenna height or individual antenna location. So it was falling here. So the breakout function, what it does this. It will actually move every sector in its own orientation. So this is sector number 1 moved in that direction and moved to the fair side or to the edge of the building. So everyone moved in different direction, and we maintain the direction, we maintain the height, we just clear it, okay? And there's many ways to clear this. But this function is called breakout, and simply you can use the rectangle tool in the software and then go to stations and breakout to get it done. But that breakout function is very useful, very intelligent. So it is really targeted. So which means you target only the stations that are a problem, the stations that are under the roof of the building, and you know for sure they are outdoor, so you have to push them out. So we can target those falling under the rooftop height, and it is precise in the sense that you push the antenna You don't push it 1 kilometer. You have control how far to push it, when to stop pushing, and where to place it and where to stop. So you can decide how far to push it, like 20 meters, 30 meters. You don't want to push it 500 meters, for example. Then it's gonna go on the completely in the wrong spot. You can put the tolerance, and then you can decide when to stop pushing. For example, you encountered a new elevation, or you encountered a clearance, or you encountered a new clutter type, like you moved from building to open. So you can decide when to stop it, and then you can maintain sector orientation. So you can maintain the orientation of the sector. So this is the breakout function, and it is very useful. So let me quickly show you the software. So I'm going to run the software and show you how that works. So I'm opening a project. This project is a small cut over Singapore, and this is just a dummy network that we introduced. So let me open the network, which is just imported. So this is the network, and then if I zoom in a bit and I display the building layer, so you can overlay the individual sites and the prospective buildings. So this is the building footprint, and these are the sites. Now, to do a breakout, first you need to do isolation. So you go object, and then you go to stations, and then you go to activation, and then you isolate by query, and then you decide, okay, I want to get only the indoor ones, following the criteria. So you see, the black ones the black sites have no problem to start with. Let me make this less busy for you as well. So the black ones have no problem. They have no problem. They are already cleared. But these green ones are problematic. So let's have a look, see what's wrong with them. For example, this site here is falling on the building, and it looks like the site height is only 10 meters. And when you look at the building height, it's here. The building height is 31 meters here. 31 meters. So it can't be. It's not possible. So you see, this is very useful. We already discriminate which one to look after. And then the second step is to break it out. So break it out is very simple. You go and highlight them, and then you go to stations, and then you go to breakout. So the breakout, I can tell the software up to, say, up to 60 meters on the building top, and then move to the nearest clutter. So once you face something other than building, and we're going to target buildings, only buildings. Let's see what happened. You see, they moved right away. So you can decide how far to move them. And you see, this is very nice now. That moved to the edge of the building, that moved to the edge of the building. So this is the breakout. It's very simple, but it makes your life a lot easier. So let me go back to the presentation. Now we're going to talk about 5G antenna. So the smart antenna, how smart it is, and how can we model it in the software very easily. So before we talk about antennas, we need to talk about beams and the type of beams in 5G. I'm not going to talk too much. We're going to make this practical and focus on the important aspects in planning when you do planning the software. So in the next radio, there are 3 types of beams, basically. We've got the broadcast beam, control beam, and traffic beam. So the broadcast is used for the PBCH, the physical broadcast channel, and the secondary synchronizations. And this is a static type of beam. So static means they are predefined positions, and they just repeat in that order, okay? So you've got 3 types of beams: broadcast, control, and channel. Now, what is a beam? What is a beam? I mean, how can we model the beam in the software? What is a beam? A beam is nothing but a synthesized antenna radiation pattern. It's antenna radiation pattern. That's what it is. Which means you can go ahead and ask the vendor, give me antenna radiation pattern for these beams based on your configuration, and they supply you in MSI format or Planet format or PLM format, so or ADF format or maybe CSV format. So it's electronic format. Don't worry about it. It's just a file that you just import. You ask about the beam pattern, and then you get it, and then we can model it. Now the good thing about that beam is it can be steered, resulting in pattern sweeping. This is electronic sweeping. So it's on the move, like here what you see on the right-hand side, it's on the move. So how can we manage something on the move where the software is going to be static? So we'll show you how we overcome this problem. So for now, beam is just an antenna pattern, which you can model. So which beam is most important for coverage, 5G coverage? I'm talking about coverage, I'm not talking about throughput or other aspects. So in coverage, broadcast beam is the most important. So why is broadcast beam is so important for our planning? Because broadcast beam is used for the user equipment initial access procedure. It's used to transmit the SS block, the SSB, which carries the PSS, which is primary synchronization signal, secondary synchronization signals, and the PBCH. All these channels, all this information are very, very important when you access the network, when you want to connect to the network, when you want to search the network, when you want to benchmark different networks, when you want to do handover. So even in the idle mode, when it's not in the connection mode, idle mode, the measurement is based on the SSS. So SSS is on the broadcast beam, very important. And also, as we'll find out later on, SS is also transmitting the SS-RSRP, which will be used to do coverage assessment or coverage estimate. So also the UE transmits the PRASH. PRASH is the first step in talking to the base station. So if there's no broadcast beam, there's no PRASH. You can't approach the base station on the uplink. You can't say, hello, I'm here. You can't do it. Okay. So PRASH is the physical random access channel, which is the procedure to access the network with first step. So all this is dependent on the SSB, which is broadcasted on the broadcast beam again. So if there's no broadcast beam reach, there's no coverage of broadcast beam, then UEs cannot connect, and hence there's no coverage. Now we established with you that we need to have the radiation pattern for the beam, for the broadcast beam, and also establish this is the way to do the coverage modeling. So how to predict coverage for the next radio, for 5G coverage? How do we predict the coverage? It's simple steps, guys. So first, you establish the broadcast beam, and they might give you individual beams. So if they give you individual beams, you have to combine them, and we'll show you how you can combine them in the software very easily. And then we have to capture the antenna beam, the beam gain for the SSB, and we have to calculate the coverage and then do the SS-RSRP analysis, as I'm going to show you very soon. So I'm going to run you a very quick comparison between 4G and 5G in terms of the beam. So I'm going to talk about the beam again, broadcast beam, SSB beam, whatever. So if you look at the 4G, the top, 4G has one wide or one fat broadcast beam, okay, which is also used for traffic and everything else. So I'm talking about the early release 9, for example. You can see here we've got 17 dBi and antenna gain. So in 4G you've got less ports, less antennas, and you have a fat pattern, and that pattern is delivering, for example, 17 dBi. Now when you look at the 5G at the bottom, it has a lot narrower. It's a lot. You've got more antennas, but it's narrower. So how is that? It's better. It's narrower. Okay, so it's very narrow, and it's delivering, however, 21.5 dBi. So it is delivering better range, but that range is mainly to solve the problem of a frequency, because the frequency at high frequencies, 6 gigahertz above, then you lose a lot of power. There's a lot of advantages of using narrow beams. We talk about it later on. But you see, this is a coverage prediction, very quick one, between 4G and 5G, and you find that 4G is not doing a good job at all. So what is the trick? What's the catch here? That's the trick. So they can actually sweep it. They can make it, they can change the orientation of this. It's electronically. You are electronically sweeping this narrow beam, which is 21.5 dBi, consistent, and not exactly consistent. You would say the edge is slightly less. But you can see when you sweep it, it's going to give you a kind of same pattern as the LTE. LTE is 65 degrees beam width. This is, for example, now is 65. individual ones are only 10 degrees, for example. So each one of these is transmitting a different SSB. Again, SSB 0, SSB 1, depending on the configuration of the antenna and how you do it with the setup. So this is guys showing you how 5G solved the problem of fulfilling the coverage size while maintaining the range that it needs. So it's by sweeping the antenna pattern, and that sweeping is running in a certain sequence and in a certain schedule, and usually it's bursty. So it's about 5 milliseconds. It's 5 millisecond. The base station spend 5 milliseconds on each beam. So let me now finally demystify this antenna radiation pattern in a smart antenna. So here we have an example, 8 beams. So 64 by 64. This is 64 by 64 antenna, and it's programmed to deliver 8 beams on the SSB, 8 beams. So let's look first at the first spot. This is the first beam. That's the first beam. The second beam, third, fourth, fifth, sixth. You see, that's what's happening. It's a swinging. It's a sweeping. So depending what a customer is, the customer will pick up the best beam, and then it will time when it's the next time it's going to arrive in my spot. So the communication would be based on that spot, on that timing. So you see 1, 2, 3, 4, 5, it's moving. And now in the software, I don't have to model it as an individual beam. In the software, all you have to do is you have to combine them into this. So this is combining every single spot or every single beam into one broad beam. And then we use this in the modeling, because you know for sure when you do coverage predictions at the 40 degrees, you know for sure that, well, eventually that spot will reach that coverage and the customers here will receive that beam. So we combine the beams. That's the trick. And that combination might be done by your vendor, or it can be done in our software. I will walk you through it in a quick demo. So how do you manage electrical and mechanical tilt in the software? So this is very important. You still have electrical tilt, guys, in 5G, and you need to be careful with it. Electrical tilt, you can manage it and in the tool. How do we do this? We do this by requesting from the vendor the different radiation patterns at the different tilt values. And then we chuck these antenna patterns in our database, and then we point to it. We point to it in the importation process. And then the software will attach the right antenna pattern, which is embedding the tilt, to the right sector, to the right antenna. You can see here, this is the red, and this is here antenna. Well, it's not exactly called red in 5G, but you can see 0, 0, 1, 1, 2, 2, 3, 3. So we can import this information. This is how we manage electrical tilt. It's in the antenna pattern, and you can import it in batch. So if you have 100 sites, no problem. 1,000 sites, no problem. You can automate the process, and then you can get it done in a matter of minutes. So this is different than the way we manage mechanical tilt. So let's have a look here. So electrical tilt, the individual patterns need to be supplied by the vendor, and the mechanical tilt can be taken care of by the user directly. So you see, this has as tilt is 0, which means there's no mechanical tilt. This is mechanical tilt, guys. So there is no mechanical tilt. There's no mechanical tilt, 0. Now, and you can see the antenna pattern is already tilted down by roughly 2 degrees or 2.5 degrees. It's already tilted down. You can see it here very clearly. Now you can add on the top of this a mechanical tilt, 5 degrees. This is further down tilting. So guys, I want you to be careful with down tilting, with mechanical tilting and electrical tilting. They're not the same. So you need to manage them properly, as I showed you. I think I'm going to skip this demo for the mechanical tilt. We have enough time for the rest of the topics. 5G numerology. So 5G numerology. This is some customers are already familiar with it. And when you add a station on the map, or when you import station, you can actually use the built-in calculator to do the resource assignment, or to do resource calculations. So this is completely automated, so nothing too much to think about here. So all you have to do, put the right bandwidth for your 5G station, put the right bandwidth, and then choose the right numerology. Okay, so you need to choose the right one. And when you choose the right one, the software will automatically establish how many RBs, how many resource blocks are in this configuration and how many subcarriers there is. And we'll also calculate for you the reference signal percentage, which you need it for the SRP analysis, and the PDFCH, the traffic channel. So this is a fully automated menu here. Let me show it to you quickly. So it's in the G0B tab here for the base station. So all you have to do, for example, if you put here 50 meg, and then you go and choose a 15 kilohertz, for example, configuration, you see you need 270 RBs, and that's the reference percentage, reference signal in the whole channel. If you switch to 30 degrees, to 30 kilohertz, which is numerology number 1, you see the values are changing. So it makes your life a lot easier. So if you want to go with 60 and 1, here we go, it will calculate for you. So this is automatic calculations done in the software. So now let's talk about the link budget calculator. So link budget calculator, also we updated this, previously was 4G, today is 4G and 5G. So we also updated this calculator to introduce different strategies for the resource, and I know some of the customers will be very happy with this. So today we can do link budget balancing, and we can consider the numerology order for 5G, and we can also apply different strategies. Because I know some customers, they, especially those who use 5G or 4G in a fixed fashion, then these guys, the equipment might have a fixed number of RBs, or might have a certain limitation on the number of RBs they can have. So you can change strategy, and then you can do link budget calculations. So this is an automatic link budget calculator. You put the parameters in, and then you put the throughput you need, and the software will reverse engineer and then tell you what is the SNR, what is the throughput, what is the planning targets, the RSRP you need in order to fulfill these requirements. And you also have these different strategies. So strategies we have user-defined RB, which means you are in charge. You dictate to the software how many RBs, how many resource blocks you're going to use. And then the software will translate your throughput that you need. So your input is throughput and RBs, number of RBs, and the software will work out for you what's the minimum signal to noise ratio you need in order to fulfill your requirements. And the signal to noise ratio is the one used in order to calculate the minimum RSRP you need in your planning. It does uplink, downlink, balancement, and so on. So another strategy is lowest SNR, minimum RBs. So this is calculating two problems at the same time. So first we find, first you specify your throughput, and then we find what is the minimum SNR that we need in order to, hang on, let's see here. So first we dictate the throughput, and the tool computes minimum SNR, then the minimum RBs. So first we establish what is the minimum SNR we need, and then we establish how many RBs we can fulfill this. So it's a kind of load balancing. The last one, we use the entire RBs to do the dimensioning. Okay, so this is what's new we have in the software, and we also have this SNR versus throughput. That's a very interesting functions, which does the translation between signal to noise ratio and throughput. So let me talk a little bit about this theory. This is adopted by 3GPP. So 3GPP instead, I mean, in any software, guys, you need to have a relationship between signal to noise ratio and throughput. How do we reach from one to the other in our calculations? So this is very important. So we decided to use, and that's been for a few months now, the 3GPP approach. The 3GPP approach is based on what's it called? It's based on the Shannon theory. Okay, the Shannon bound. So this is the gray one, is the Shannon bound. That's the theoretical limit. Okay, and we know this is not practical at all. So what you need to be doing, what you need to be using a practical estimate, an estimated reality. So estimated reality. So what we do, we have some sort of fudge factors. The fudge factors along the way for different signal to noise ratio. We apply corrections. Correction here, correction there. Okay. So we apply corrections in different spots along the way, and that correction is called the scaling factor, Shannon scaling factor. So you see, it's a polynomial. So that polynomial multiplied by this theoretical line, which is an equation effectively, if you multiply these two, you get the effective throughput, or you get the effective relationship between signal-to-noise ratio and throughput. So this is an excellent way, a very elegant way, in order to have one equation to solve the problem of estimating throughput or estimating SNR. And that's what we did in the software here. So these different attenuations that we need to apply and correction terms are applied here in the software. So you don't have to complicate yourself. You just need to select the technology you're working with, and the software will extract from the database the correct attenuation or correct fudge factors in order to correct the estimate. And one thing here I should note to you, we introduce layers. Layers, we're talking about multiple spatial layers. And this means that you can double the throughput or triple the throughput because you have multiple spatial layers in your link or in your antenna. So if you put it to auto, the software will pick up the value from the base station, so that you can set up the layer, how many layers per station, depending on the antenna capability. So the bottom line is, this is a function, in this built-in function in the software that will take care of translating your signal-to-noise ratio into a throughput and vice versa. So now let's talk about the SS-RSRP, the SS-RSRP predictions, which is the coverage. So let's have a look here. So SS-RSRP, what does it mean, SS-RSRP? So in 4G, guys, we only had RSRP. Our life was easier. It was only RSRP. Now today we have a broadcast RSRP, and we have a user-specific RSRP. And there's so many of them. Okay. So the one I'm really concerned about in my modeling is the SS-RSRP, which is the secondary synchronization reference signal receive power. Now this SS-RSRP is carried by the SSS. Sorry guys, so many abbreviations. Okay, by the SSS, which is the secondary synchronization signal. So this is the middle 20 RBs. It's the middle 20 RBs. So the 20 RBs in the middle of the channel. Okay, this is where the broadcast is happening. And as you know, guys, I mean 5G can be 100 megs. So it's not really straightforward for the UE to scan, for the UE handset to scan the entire channel or the entire band. So the base station or the UE have to only scan the middle of the band, the middle 10 megs, middle 10 megs of the band. So the middle 20 RBs in the channel will be the ones to target, to establish information about the broadcasting station. So it's the only valid way to compare signal levels from individual cells and different operators. Okay, so if you want to do drive testing, you want to do validation, you want to do a comparison between different operators, you have to use the SS-RSRP. Okay, but it's the only valid way to do comparison. So this SS-RSRP is very important for cell selection, is to choose which site to camp into, and for handover. So they estimate the next station coverage. So it can be measured by draft test tools, and it doesn't require connection with the cell. So you don't need, for example, a SIM card or to be connected in a connected mode with the base station to measure SS-RSRP. So it is very, very useful. So this is some equations here to show you how you can derive reference signal, but it's not very interesting for me. What's interesting here is that the SSB beam is important. The SSB beam gain. So very important we establish the beam gain from the broadcast beam, and that's to be used to predict the RSRP coverage. So in the software, that's the way we talked about the percentage here. The software, you put the bandwidth, you put the numerology, and the tool will calculate the reference percentage. Okay, and this is what the software used in order to estimate the SS-RSRP. So this is done by the tool, and this is the function coverage network analysis, RSRP analysis, RS, and then the tool will give you the coverage. So let me show you how that works. So this is a network I have on the map now, and then you go to coverage network analysis, RSRP, RS composite coverage, and then the software will show you the RSRP, will calculate the RSRP for you. So this is the RSRP, and you can see here on the bottom, or you can see the legend here on the top. So we've got a neg 110 dBm to neg 70 dBm and above. So you can see the coverage range on the top on the map. So here take this opportunity to show you quickly how do we run coverage predictions in the software in a very, very efficient way. So I have here a computer server. So this computer now, I've got how many sites? I've got nearly, guys, 792 sites. I've got a lot of sites. Now let me show you how coverage predictions take care in the latest release of software. How fast it is. So if you have like 1,000, 2,000 sites, you can really speed up the process considerably. So you just go to the database station. The database station. You select the station database you have for your 5G network, and then you run remote simulation. A remote simulation, I can do multi-core processing. So I can do 8 sites, 8 cells at the same time, calculate the coverage for 8 sites concurrently in parallel fashion. So even I can do 10, 12. So you see here, the software is recommending 12. So I'm gonna do 8 sites at once and run a simulation. This is a really, really useful function that really pays off when you are dealing with a very tough deadline and you have massive network. And we are talking about 5G, and we're talking about high resolution data set. So high resolution is 2 meter step. So if you're doing this for 2 kilometers, if you do it one by one, it can take it 2 days or 3 days to do a small network. But with the multi-core, you see what the software is doing. The software is automatically opening multiple sessions automatically. This is, guys, a state of the art, and I'll show you how fast it is. It's going to run coverage. Here you go, started. So you can see 1, 2, 3, 4, 5, 6, 7, 8. 8 sessions running concurrently, and the software is calculating the coverage like thunderstorm. So you can see how fast it is running. So I bet, guys, this is going to finish the network in a matter of 4 minutes or 5 minutes, even if it's 700 something, and even if it is high resolution and 2 kilometer radius. So once it's done, the software will put the coverage in one place. Let me show you the CPU, guys. So that's what the CPU is doing now. You see, it's still the CPU is relaxed. The problem is capping around 30%, but it's still relaxed, which means I can still run more threads. I just capped it to 8, but you could run actually more, depending how many licenses you have, and depending on your computer memory, and how many applications you have open at that time. So I'm going to keep this running, guys, in the background. We'll come back to it maybe later on. But now you understand how it's possible to speed up coverage predictions when we talk about carrier grade network with lots and lots of sites. The analysis is here, coverage network analysis, and then you go to RSRP, and you've got here the servers, which is first server, second server. This is a redundancy analysis, and that's overlap analysis, and so on. So let me go back to the presentation. Now, statistical analysis, guys, like I said before, the tool has a GIS dimension, and it's going to make your life a lot easier. You don't have to have someone who is experienced or specialize in GIS to solve your problem, to do some basic math. So let me show you how we deal with the outdoor coverage. So usually carriers or operators are interested in outdoor coverage as the main criteria. So outdoor means road, so people on the road, on the streets, and so on. So we can import this information, the GIS information, into the software. And you can see here on the left-hand side, I have highways, motorways, and so on. And you can have points, polylines, polygons, and so on. So, however, these roads are coming as a center line of the road, just a center line. So if you want to be more accurate, you can analyze a signal along the road as a center line of the road. But if you want to be more precise, you need to buffer the road, buffer in each direction. So you offset the road center line in each direction. And then you have a kind of a polygon now. So it gives you better estimate. Now in the software, we have a function called filter. We've got map filter, general filter, and that general filter has the capacity to check vector line limited. So you can limit your analysis, your statistical analysis, to the vector line only. And you can put a buffer So here you have a buffer 2.5 meter each side of the road, each side of the center line of the road. You can buffer it 2.5 meters, and that means you're going to analyze area, not a line anymore. So let me show you an example here. So you see, this is two road center lines. So you've got the left lane and the right lane, and you see they've got more, sorry, not the lines here. It's different stream, upstream, downstream, and then every stream you have 1, 2, 3, maybe 3 lanes or 4 lanes. So what we need to do, we need to do this. We need to flatten it. Okay, I'm not talking about flattening the curve. Okay, we just need to flatten this center line of the road in order to have more pixels, to have more samples along the road. So let me show you how this is done in the software. So in the software, you display your RSRP. You have your vectors on the map. This is your RSRP. So I'm going to apply filter on RSRP, and then I'm going to add the roads and the streets and the highways, and then you go map, filter, general filter, and then use the general filter. Check the vector line limited, and check the distance you wanna use. Put the range, the RSRP range in dBm. Say from -109 dBm to -30 dBm range. Compute, and that's it. You got the results. But trust me, guys, if you're going to do this in the JS software, it can take you 1 day. It can take you 1 day to unless you're very experienced with JS softwares. Okay, so you can see here, and now we have 68% of the roads in that map are actually enjoying -100 dBm or better RSRP, -100 dBm or better. So that's what it means. So it makes your life a lot easier. And when you apply the filter, that's what the software is doing. The software is cutting the coverage along the road line, along the vector line or the center line of the road with a buffer of say 2.5 or 3 meters. Okay, I'm not going to talk about, I'm not going to do a demo for this. So smart antenna. In the software, guys, today, in the software, you see here we have, when you want to model MIMO, massive MIMO, beamforming, whatever, you see in the software today, we have capacity to model the layers and model the number of arrays and the multi-user, how many users, concurrent users. That's a massive MIMO. So you can model how many users, concurrent users, how many spatial layers, and how many arrays. So arrays, we're talking about these arrays, okay? So you see this traditional antenna, you've got here only 1 array. You can only make 1 beam. You've got 2 arrays, you can make 4 beams. And that's an array, you can make even more beams. Okay, so you can see we can make more beams here with the bigger size antenna in 5G. You can have more beams. More beams means more directional, more narrower beam. The beam will be narrow and will be a higher gain. I will give you better performance overall. It also means you can handle more spatial layers. You can handle more multi-users. You can handle more multi-users. There's a lot of advantage in this. So you can see here in the software now, we can have a station or cell-specific MIMO configuration. Cell-specific MIMO configuration, and then you can decide on how many layers. Now, don't mix the arrays with the antenna configuration 64 by 64 or 32 by 32. So 64 by 64 has up to 8 arrays. 32 by 32 has up to 4 arrays. Okay, you need to put the right numbers here. And this information you usually get from the vendor, from the equipment. So layers are the number of spatial layers, and then you've got how many concurrent users you want to serve. That's where you set up the information. So after that, once you have the configuration in every station, you can do a throughput analysis. Okay. So you see here we introduced this has been here for a long time ago. The throughput map, and then we have here different MIMO configuration, AAS, adaptive antenna scheme. Adaptive antenna system, we have spatial multiplexing, which means you're going to activate multiple layers. And here we have multi-user MIMO, you're going to activate multiple user. Here we have transmission diversity, you're going to use multiple antennas to provide diversity. And then here we have the traditional on the end. So you can configure it in the software to operate in MIMO fashion or non-MIMO fashion, and what type of MIMO you want to operate it on. And here we have the throughput. So you can map the signal to noise ratio into throughput automatically, but by the use of the Shannon theory, Shannon bound. corrected channel bound, should say. So here you can define this as auto, and auto means it's going to use the individual parameters you have on the site. If you dictate it to 2, for example, so you're going to use 2 spatial layers everywhere. So it's going to double the throughput effectively. So massive MIMO configuration. It's beamforming for traffic channels. So beamforming, this is what we talked about already, spatial multiplexing. With traffic channels, you can do beamforming traffic channels, you can do transmission diversity, you can do spatial multiplexing, you can do user multiplexing. So this is an example here. We'll quickly show you what happened when you use 1 layer and 2 layers and 3 layers. This is 1 layer only here, 1 layer. I'm using 5G configuration. So you see maximum I'm getting is 138 meg, 134.8 meg, 134.8 meg. When you use 2 layers, I'm getting 269. So I'm scaling the entire network. That's why the coverage is not changing much, because I'm scaling everything equally. So 2 layers, I'm getting 269 meg, 269 meg. With 4 layers, I'm getting 539 meg. Okay, so this is where 5G is very, very powerful. Is that the number of spatial layers you can multiplex on the same channel. So multi-carrier aggregation, the software also does support multi-carrier aggregation, which is combining maybe 4G and 5G, or 5G and 5G, or 4G and 4G. So the idea is to connect different bands or different different channels from the same band, and then work together in an aggregated fashion. So multi-carrier aggregation is based on master-slave relationship. So it is supported in the software. You need to specify the master as a pilot. So the main station, which is doing the control, need to be a pilot. And then all the rest of the cells who's going to be aggregated together with the master need to be on the same group. So the master-slave relationship must be existing by checking the pilot, and you need to follow the same group. You need to be the same group. And once this is done, in the software, you can run multi-carrier aggregation. And probably multi-carrier aggregation might have showed it to you before. It's here, carrier aggregation in the throughput. So when you check this box, the software will look at the master and slave relationship between the sites. So let me show you an example here. This is no carrier aggregation, no carrier aggregation. You can see the coverage at the edge. The edge is a bit weak at the edge. The throughput. This is throughput map. So throughput map here, you're getting green, red in these areas. You can see here green and red, mostly green, and you can see the green is at the lower end of the throughput. Now, once I run the simulation with multi-carrier aggregation, so I'll show you what happens. So the software only show you what you need to see. Okay, it doesn't show you everything. Only show you the master cell. So the rest of the cells are just auxiliary in that case to the master cell. So if the master cell has a coverage, then we overlap the coverage with the serving cells, and then we add the throughput. Now look, this is a green. This is now red and yellow. So you've got now more throughput at the edge. At the edge of the master side, you've got more auxiliary throughput because of the multi-carrier aggregation happening between the adjacent cells and this cell. So this is multi-carrier aggregation, and it can be done and managed in the software without any problem. Neighbor planning, quickly, we don't have much time now. So neighbor planning is also supported in the software. So the neighbor planning is based on the handover surface, or the handover map concept. So you can see these pink areas here are actually, we call it the handover surface. Handover surface is defined as the both signals, A and B, must be above threshold, and if you take the difference of these two, the two signals, the absolute difference is above 5 dB. So this is the area exactly, the pink. Now, the more pink you have, the more likely this is a good neighbor. Okay, so in the software you can define what is the handover target, the handover margin. You can define the RSRP, and you can define the surface, how much pink you want to have, how much handover area you need to have to be satisfied as a good neighbor. So you can see here, this is a bad neighbor. These two sites are this far away, and this is 5G, both of them. And you can see not much pink between them. So they're not a good neighbor at all. So the software will not create neighbor lists for this too. This is an example of a good neighbor. Then the software will pick this two as a good potential neighbors for handover. So this is where in the software you can calculate handover and neighbor calculations, and you can define the parameters, and then the software will calculate for you for every cell who is the neighbor. So for every cell, you will know what is the neighbor list. And you can see here, this station, cell number 778 has 1, 2, 3, 4 neighbors, for example. And it become part of the station parameters as well. If you go to the station tab, the G0B tab in the base station, you can see the neighbor list here, and you can see who they are. So the coverage that you produce, you can publish it online. You can publish it online. This is an additional tool we have in the software. It's a very, very smart architecture, and it's a very secure and also very powerful. So this engine allow you to export from H to Z coverage or other parameters like vectors or RSRP analysis, SNR, whatever analysis you produce, you can dump it into a cloud server, and the cloud server will take care and then pass it to WMS server and publish it online. Okay, so this design has a load balancing capabilities, and it's secure. So let me show you how it works. Click on this. So I'm going to log in. So I've got Singapore account. Log in. So here you go. This is map of Singapore. And then you see I have in this project you have 1, 2, 3, 4 layers. I can activate the RSRP. Here we go. You see it's very fast. And you can publish the coverage in different colors, 1 color or 2 colors or no colors. You've got flexibility how you want to export this. It works in the same way that Google Map works. You can zoom, the more you zoom in, the better the quality. So if you zoom in, you get a better quality map. You've got satellite view or you've got map view, so you can do RSRP. So you see, initially you have a low quality, and then when you zoom in, you have better quality, and it's very fast, very responsive. I have on the left RSRP, I have server coverage. That's the server coverage, which is the normal server coverage. You can see this is bigger and also fast. And I also have the sites. I can put the sites on. And I have the roads. So all the GIS data you have, you can publish it online in any order, and you can put any layers you want. You can have a public link, or you can have a private link. So you can also inquire, guys, about this service if you need anything. So you can put address here. For example, if you search for an address, you can search for an address, it has autocomplete, and then it will take you there. And then you can display maybe the coverage in that spot. This is the spot. You see there's no coverage in that spot. All right, so this is, guys, pretty much what we wanted to talk about. Thank you for your time. And Farad, if you want to conclude.
Sure. Thanks, Yahya. So I hope it was basically a good session for you, and you took away some basically some pointers from this presentation. There were some questions that you might have seen during the presentation, and I think that one of the most popular one was to do with the multi-core feature, and just emphasizing that multi-core feature is something that basically comes with tool, it's not extra, and all the limitation is to do with the number of licenses you have. So it is you don't need extra hardware or anything like that. It will use the number of licenses available to you, and will run that many stations at the same time. So that is the multi-core feature. And now this presentation will be available soon. We'll be having another presentation tonight, and I'm assuming that soon after we can basically make this presentation available to you. You know our email address. Please don't hesitate to get in touch with us if you want more information or extra questions. Thanks again for your time, and looking forward to catching up with you soon.
Just one more thing, guys.
Yes,
So the multi-core or multi-core, multi-session, it's available to every customer. It's not something that you need to have on demand. It's only a question of how many user license you have. So if you have if you have 15 licenses, for example, on a server license, then you can have up to 14 concurrent sessions, up to 14 calculations. Okay, you can have 15 sessions, but it will be 14 calculations, up to 14 calculations. If you have the standard license that we have, which is standalone or soft standalone, it can do 3. It has a 3 sessions, but effectively it's 2 because you need 1 session to run the process, and then you have 2 sessions for the calculations. If you have, so it depends. Anybody have access to this feature? It's only a question of how many licenses. I mean, so obviously the more licenses you have, the more horsepower you can do. In terms of computer specs, you definitely need to have more RAM. Definitely you need to have more RAM. And what I found, Xenon CPUs doing a better job than i7 CPUs because they are scaled differently. So a normal Xenon CPU, probably you can see the specs on my computer here. My CPU is like a 2.1 gigahertz. It's not incredible machine, and but I've got plenty of RAM. I think I've got 32 or 64 bit, 64 gigabyte of RAM or something. So yeah, I've got 64 gigabyte of RAM. So RAM is important because the software is going to run multiple sessions and going to manage the memory in different sections. So this is very important. You have good RAM, and the CPU, like I showed you guys, this computer is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 by 4. So this computer didn't actually reach 30% with the 10 sessions or 8 sessions. Didn't reach 30%, which means you can still do more as well. All right, thank you guys for your time. I appreciate it. If you have any questions, please do contact us, and we're more than happy to follow up with you today. So thank you for tuning in, and then we look forward for the next session.